So thank you so much, everyone, for coming today. I wanted to talk today a little bit about space sails, and specifically about how we can go from where we are today to where we can be with interplanetary and interstellar solar sailing and other space sailing missions. So to start us off, I wanted to talk a little bit about a symposium last year on large area structures and light, where many different concepts were discussed and synergies between different types of space sails were also elaborated on. After this, an international working group was established, and as part of this, we look into using these synergies to advance the technology of space sails and go from where we are today to these interplanetary interstellar missions. As part of this working group, we also published a database on space sails for the state of the art, as well as a historical review and future outlook of space sails. The aim of this paper is to look at the synergies and to look at how space sails can be used to meet the exploration goals of space agencies. So at this point, it was necessary to ask two questions. Firstly, how big is the technological gap between the state of the art today and the future proposed interplanetary and interstellar missions? Secondly, how big are the risks of going from what we have today to what we want to do in the future in interplanetary and interstellar missions, and how can these bottlenecks be overcome? So to answer these two questions, we chose two methodologies. Firstly, we wanted to do static technological assessment using standard multiplicative scaling of system parameters. And secondly, we wanted to look at dynamic technological assessment, so technological risk. And for this, we chose to use the advancement degree of difficulty. Essentially, this is very similar to TRL, but there are some key differences. Firstly, low AD squared looks at low risk, and high AD squared is high risk. Also, there's a key difference that AD squared also looks at cost, schedule, and the experience base of the stakeholders. So to be able to effectively compare the state of the art with the future proposed missions, we chose 3 case studies. So firstly, we wanted to look at Solar Cruiser, which is a large solar sail proposed by NASA for heliophysics studies at a sub-L1 orbit. We also chose Project Svarog, where I'm the lead engineer, and there we want to send a solar sail as well. We want to do sun diving and eventually achieve solar system escape within a few decades. And finally, Breakthrough Starshot, where the aim is to reach our closest star system within a few decades using a ground-based laser, as many of us are familiar with. So a bit more about the system design for each of these 3 missions. So we have that Solar Cruiser basically has a very standard small satellite type mission design with many CubeSat or COTS type components. And the sail itself also has a lot of embedded systems. So we have the photovoltaic cells as well as the reflectivity control devices. For Project Svarog, we have a similar design, but now it's in CubeSat form, and the sail does not have any embedded components. And finally, for Breakthrough Starshot, all the components are embedded onto the sail, and it's a laser sail. It's very thin, very lightweight. So now on to the results. The first part of the results, to answer the first question, what is the gap between what we have today and where we need to go? So to be able to characterize this, we used, as I said, multiplicative scaling factors. What I mean by this is, for example, for the area, scaling the area of the maximum area of the state of the art with what is required for each of the missions. And the results are given here on the right. The parameters we chose are characteristic for light sails, and the main one being the sail loading, or the mass to area ratio. So if we look at the max column here to the right, we can see that the expected trend is that the scaling increases with the complexity of the mission. However, it does not increase linearly. And this is interesting because it says that we can reach very far and go to very interesting destinations without scaling an excessive amount. It should also be noted that this scaling does not apply to all parameters. For example, the area, we can see the scaling actually decreases with increasing complexity. And this has to do with the fact that we are trading mission elements. instead of using a larger area, we are looking at a greater photon pressure. So, for example, by using sun diving or a ground-based laser. So to answer the second question, we wanted to look at risks now. For this, we did a full AD² study for all the 3 missions, and the key risks are given in the following slides. So firstly, for Solar Cruiser, a lot of these studies were based on the work done by Johnson et al. For AD². And the main risk was seen to be the attitude determination and control subsystem, specifically the use of RCDs. And this is given the fact that RCDs haven't been used in deep space on NASA missions before, and therefore the AD² is relatively high. However, there were further plans for testing before funding was frozen, and this would have decreased the AD² of RCDs. So for Project Svarog, we have more risks, and the risks are also greater. Firstly, we can see that the sail deployment mechanism is quite a large risk. We are using metallic booms currently, and we have manufactured a prototype of 3 by 3 meters. But scaling this up to the size we need, about 20 by 20 meters, could introduce further risks, and therefore it might be necessary to switch to a lighter design, such as composite booms or possibly even spin deployment. Another risk is the ADCS subsystem, where we're using passive stabilization, so no active stabilization during the trajectory. And this has been proven numerically, but hasn't been proven experimentally in deep space. Therefore, it might be necessary to use RCDs or conventional ADCS, but these might again increase the risk further since these are complicated systems. Finally, the power on board is also a big risk for us. We're using deployable solar arrays, which have been proven to work in the destinations we're looking to fly into, even very close to the sun. However, given our limited experience base with actively cooled deployable solar arrays, the AD² is quite high. So one solution is looking at other parts of the spectrum of space sails. So solar power sails, what we're talking about with embedded solar photovoltaics. But instead of embedding them, we could use them as flexible extendable solar arrays, and this could minimize the risk quite a lot. Finally, the system level risk is quite high, as I mentioned, the experience base and the funding, and we are tackling this currently with incremental testing. So we had a ballooning mission a few weeks ago, tested our solar sail at 27 kilometers, and we also want to continue testing with low Earth orbit launches, hopefully in the coming 2 years. So for Starshot, again, the risks are quite high, and these are the main risks identified from the study. So the sail material, in terms of thermal management, there are quite high risks because the absorptivity is quite low of the current suggested materials, but the emissivity is still not at the required levels, according to the author's knowledge. And alternative materials have been proposed, as well as coatings. So there are other options available, and this is an active field of study. The ground-based power, of course, a large risk, given that nothing of this size has ever been built before. And although the technological risks aren't great, because each component can be manufactured and scaling it up isn't the largest issue, there are economical risks and political risks. There are alternatives available, but these also present further risks, such as because having a space-based laser could have further economical and political risks, and having lower accelerations, for example, sun diving, could mean a longer travel time, which could, for example, pose higher mass restrictions again. Finally, the ADCS subsystem, the plan is to use an LED-based attitude control system, and this hasn't been prototyped and tested, especially not in deep space, and therefore the risk is still quite high, but it's reasonable that with further work, this risk could be decreased to quite low values. So to conclude, I wish to go back to the 2 questions asked at the start. So firstly, we can say that in terms of scaling, near-term interplanetary missions like Solar Cruiser can be reached within half an order of magnitude scaling. High delta V maneuvers and missions incorporating those can be reached within about 1 order of magnitude. And finally, other stars can be reached within 3 orders of magnitude. So in terms of the major risk areas, the shared ones are from the study can be seen to be the ADCS subsystem appeared in all 3 missions. The sail material very important, especially from a thermal management perspective. And finally, something extra important to note as well from not necessarily from the 80 squared study, but from looking at the system designs is the subsystem integration, because adding the different components together also increases the overall risk, especially seen by the ground-based laser array. A couple of general conclusions as well. So technological maturity and technological risk aren't necessarily the same, and this is illustrated by the diagram on the right-hand side, where we can plot different technologies on TRL versus 80 squared scale. So we would expect that technologies with high TRL show a low risk and low TRL show a high risk. But this isn't always the case. And this is especially because of the experience base of the stakeholders. For example, for thin film RTGs planned to be used on Starshot, these are relatively low TRL. The efficiencies are really low, and they have been prototyped, but they haven't been flown in the intended destinations. And the risk, however, is relatively low as well, because there's supposed to be a lot of funding as well as experience of the stakeholders working on this in Starshot. For actively cooled solar arrays, again, these have been flown near the sun, but given our lack of experience with these, the risk is still quite high. Finally, it's also important to note that international collaboration was seen to be a very important aspect of mitigating risk in all of these missions, partly seen by looking at technology transfer from other portions of space sailing, but also looking at other areas and other industries even. For example, developments in electronics and the biomedical industries have led to improving technologies in this field as well. So with this, I wish to conclude by thanking Imperial College and specifically the Old Centralians Trust for making this possible. And also I want to thank everyone in the room for your time. I'll now open up for questions.